Right. So we are looking today at change in linear functions. And one of the things we're looking at is comparing linear and exponential functions to arithmetic and geometric sequences. So if you remember from the last class, we learned that an arithmetic sequence behaves and looks like a linear function. Geometric sequences behave and look like an exponential function. And here's a couple of key formulas for you to work with on this one. So we saw last time the formulas for the arithmetic sequence, and here's to the kth term. Most of you are familiar with slope-intercept form, but some of you are not so familiar with point-slope form of a straight line. Point-slope form is actually better for a straight line. So when you introduce linear functions, you introduce it with slope-intercept form, because this is really useful for moving between a drawn graph and an equation. But when you're moving between 2 points, if you're just given algebraically 2 points, it's much quicker to use point-slope form. So we'll practice that a little bit later, but today just reminding you of this one. I know that some of you know that form and some of you don't. So in geometric sequences, they behave like exponential functions, and the two formulas look like this that we saw last class. An exponential function, this is the typical one I use for an exponential function. And it's written here as the movement between 2 points as well. But I tend to solve most of my problems with that one. Okay. So it's important to recognize some of the similarities and some of the differences between the two. So we have our functions for the linear function and the exponential function. Now, this next bit, all but one of you, I think it was Zane from the other class, all but one of you lost half a point because when we were looking at the question with the quadratic in the test, in the major, you found that the second differences were constant, and you get half a point for that. The actual correct answer uses the phrasing. So you're going to have to memorize this phrasing. Over equal length input intervals. All of you in this room missed that part of the phrasing. You only said that the second differences were constant. You would have to say over equal length input value intervals, the second differences are constant. Don't make up your own wording, because usually you get it wrong. There are some bits that are worth memorizing, and so I'm going to really highlight that here today. When we're trying to justify something being a linear function or being an exponential function, these are the phrasings you should use. You should use no other phrasing. There's a few bits and pieces of the phrasing, like when we do limits. As x increases without bound, the function increases without bound. This type of phrasing, we have to learn to include that. So a lot of you, I let it slide on the major this time, but I won't next time. With the limit question, if you don't give the worded answer as well as the limit answer, you're going to lose the point.
Already AP MCQ results from like the AP classroom going to be released?
When everybody has taken the test. I'm waiting for one student still to take the test.
What, the vision?
Yeah. Okay. Let's focus now on today's lesson. I'll take questions at the end that are about other issues. So one of the things that we can tell about a linear function is it's all based on addition. And with an exponential function, it's based on multiplication. If you have 2 points, you can write an equation of a linear function, an exponential function, or an arithmetic or geometric sequence. All, if you imagine it, it is possible with just 2 points. You can't tell the difference. If you've got 2 points like here and here, you can draw a straight line through these points. You can also curve an exponential function between these 2 points. So you're going to need more than 2 points to tell the difference between these type of functions. Or if you're asked to put a linear function through it, then you can do it through 2 points. Okay, our first question. We've got some selected values in each of these tables. We're going to try and justify whether this is a linear or an exponential function. So this first one, is this one going to be linear or not? Let's have a look. What is the change in the y values here? Here, -2. And how about here? And what about here? And what about here? -2. So I meant to delete this bit. That's on the next page. So let me see if I can zoom in a little bit somewhere so I can write it. So what was the phrasing? For equal length input value intervals. Input value. Yeah, intervals. When I say learn to use this exact phrasing, if you don't learn to use this exact phrasing, that will be bad. So what happens for equal length input value intervals?
The function increases constantly.
Let's go back and read. The output values change at a constant rate. We're memorizing these ones. Okay, let me have everybody read this one out. Read this one out loud. Now let's hear Arnav, who didn't say it. Sorry, Arnav, can we read this out loud?
For equal length input value intervals, the output value should change constantly.
Thank you, Arnav. That will do me. So, what is the answer here? For equal length input values, the output values change at a constant rate.
So if I said constantly instead of a constant rate, would that still be wrong?
Okay. Which bit of memorize this phrase exactly don't you get? Do you know what exact means? Okay, well, we're going to try and... I actually hate this. This is not good learning, but this is... yeah. This is going to be useful for taking this style of an examination. It's not IB. All right. Okay, so how about this one? What do we go up by? What does that mean? Oh, you can see it's quadratic, can't you, on this one? Yeah. In fact, you can see it's quadratic quite clearly because those are the square numbers, aren't they? 1, 4, 9, 16. Those are the square numbers. It's not going to be exponential. We can see this one. So, no, not. This one's, it's quadratic. We were only asked in this question to determine if the function was linear or exponential or neither. So I would say, let's give the wording back that they asked for, neither. And I'll give my explanation. All right, let's try these ones. See. What are we going up by here? 1, 2, 4. So can we see, so we can see it's not going up in a linear pattern pretty quickly. So let's look to see if it's exponential. What do we multiply 1 by to get to 2? What do we multiply 2 by to get to 4? And what about 4 to 8? What about 8 to 16? Okay, so what type is it? Exponential.
So what if you did the differences again and you got the differences to be constant? That's also exponential. Right?
No, that would be quadratic.
No, it's the third differences.
Cubic. Exponential won't give that type of a pattern. All right, so what's the reason? All right. let's go back and do our reading. Everybody read. Everybody read this one. Arnav, sorry, pause a second. Can you not do that? Don't tie that around your neck like that. Okay, put it down. Put it on the table. Put the choking device on the table. Now, if we can read, please. Okay, let's see if you can remember that for 30 seconds. Let's try again. Thank you. Proportion 8. Did I miss it? I missed a letter. It's an E. I'm missing an E. Proportionately. All right. Well memorized. Please, let's memorize these phrases. All right. How about this one? Clearly, it's not linear, is it? So, how much are we going down by here? What do we multiply 80 by to get 20?
But they're not equal length input intervals.
What about this one? What about this one? Okay, so it's different. It's
10 instead of 5. It's not equal length.
Notice here, so there was a question on one of the two majors like this one where one part of the input values was messed up. And so check your equal length input value intervals. Notice here that this one is not equal to the other one. So if we just ignore that one, we see that it's a half for the others. This one's twice as much, which is why it's a half times a half. So this interval here is different. This is by 10, whereas the other ones are by 5. So does that mean that this one is exponential or not? Yes, it's exponential. Can anyone tell me why it's exponential? Now, this is a hard question. There's a bonus here for anyone who can get it right. Why is this one exponential? Let me hear further.
Over equal.
I'm only going to take the smartest kid in the room.
The output values.
Any, go on, have a go.
Over equal length input intervals, the output values change proportionally.
He missed a word, didn't he? Input value.
Oh,
Close. You were close, so half a point for that one. So, who can tell me the correct wording? Pervert, the smartest girl in the room. Let's hear it.
Over equal length input value intervals, the output values change proportionally.
Oh, excellent. You must be really smart, unlike these other people who don't seem to be able to manage such a challenging question. All right, yeah. I wonder if I can just do a copy-paste there on that one today. Duplicate. There we go. Oh, I like that. All right. Okay. Work together with your partners. Have a go at this one. I'll give you 4 minutes for this question. Okay. So we're trying to solve this problem here. What we need to do first is we need to figure out what our constant ratio is going to be. So we got a few bits of piece of information here in the question. Let's extract that first. We're told that there are 43 on the third day. This means that the third term in the sequence is 43. We're also told that there's 140 people on the 6th day. So the 6th term in the sequence is 140. We're asked to find the 10th term in the sequence. There. So first up, we need to find the constant common ratio. So we can say that A6 is equal to A3 multiplied by 3 lots of the common ratio. So we get this equation. Putting in our values, we get 140 is equal to 43 times r cubed, which means that r is going to equal 140 over 43, and then we need to cube root that. I'm going to leave it like this because the answer is going to come out approximate. We won't use the approximate answer. It's about 1.48. Let's use the exact answer as given there in our model. So this means that the nth term in the sequence is equal to, and we can use this other formula. I'm going to use the other formula for this one. So I'm going to use from 140 up to, and then let's use the r value like this. And then we need 10 minus 6 over 3. So that's going to be 140. There's our r value. And we need to the 4 over 3. So I can put that into the calculator, calculate that one. Oops. 140 times, and then I'll do a bracket, I'll do a quotient. 140 over 43 to the power of, and then I'll put it in another quotient, and we want 4 over 3. Press Control Enter to get the exact answer. I've got mine rounded to the nearest integer because it's a person. So I'm rounding up to the nearest integer. Will give me 676. Let me just check the decimal expansion on that one. Change my settings. Document 7.2. And then change to float. We can see it's 675.5758. So 676 people would seem like a suitable answer. Okay. Let's have a look at the next question. Give you 4 minutes for this one. It's a little bit easier. All right. So let's extract our information. Here in the question, we're told that the 5th row is 31. So that means that A5 equals 31. We're told that the 11th row is 49. So A11 equals 49. And we are asked to find the 25th row. So we want find A25. We're also told it's arithmetic. So the first thing we need to do is to find out how many lots of common difference will take you from from A5 to A11. That's going to be 6 lots of common difference. So we put our numbers in, we get 49 equals 31 plus 6D. That's going to give us 49 minus 31, 18 equals 6D. D is equal to 3. So we can find out what the A25 is. If we start at A11, how many lots of D do we need to get from 11 to 25? So we need 14 lots of D. So that is 49 plus 14 lots of 3, which is going to give 91. What's the units? Seats. Seats. All right, to finish off today, we have an exam style question. We don't have a lot of time today, so I'll go straight into the exam style question for you. So a certain car is initially purchased with a purchase value of 20,000. If it loses 9% of its value each year, then what is the car's value after, when is the car's value 10,000? So we need to set up our function, we'll call it v of t. What's our initial value? 20,000. What's our common ratio?
9.
So how do we make 9% decrease?
0.91.
Mihir over here? 0.91. So what we want in here is we want a, let me show it a little bit more because not everybody seemed to know that one. We want 100% minus 9% every year to the t. So 100% is equal to 1. 9% is equal to 0.09. So this gives us our common ratio or our change factor of 0.91 to the t. So if it goes up, add the percentage to 1. If it goes down, take the percentage away from 1. So we need to solve this. So we're going to use nsolve. So on your calculator, you want to use nsolve. And then you can type in the equation 10,000 is equal to 20,000, 0.91 to the t, and then comma t. Type this into your calculator. It should give you the answer. So just doing that on the calculator, we're going to get... So menu, algebra, nsolve. I don't have to write 10,000 and 20,000. I can put 1 equals 2 multiplied by 0.91 to the power of t, solve for t. And we see that we get, this implies that t is approximately 7.35. So the correct place we can answer is between the 7th and 8th year, it will lose to this value. Okay, let's just finish there for that.